On November 17, 1911, the Royal Society of Sciences in Göttingen received a thin, unassuming scientific paper. Its author was Otto von Bayer, a German physicist known for his work on cathode rays and X-rays. The paper, titled On the Intensity of Röntgen Rays, detailed his meticulous experiments with newly developed X-ray apparatus, a tool just 16 years old. It promised a measured advancement in understanding radiation. What it contained, however, was a single sentence that would lie dormant for decades, a ghost in the scientific machine. Von Bayer's research focused on the quantitative aspects of X-rays, their intensity, their generation, and their interaction with matter. This was the cutting edge of physics in the early 20th century. Universities and research institutions across Europe and America were racing to unravel the mysteries of these invisible emanations. The era was one of profound scientific discovery, with radioactivity, quantum theory, and relativity all emerging around this time. Von Bayer's paper was a small contribution to this grand, unfolding narrative. The crucial sentence appeared in a footnote, almost an afterthought, buried deep within the experimental results. Von Bayer was discussing the immense energy required to generate these X-rays, noting the electrical potential differences involved. He posited that if an atom could somehow release its constituent parts, the energy liberated would be truly colossal. It was a speculative leap, divorced from his experimental data, a fleeting thought on the ultimate source of atomic energy. To understand the context, consider the state of atomic theory in 1911. The atom was still a relatively new concept, with Rutherford's nuclear model only established in 1911 itself. The electron had been discovered, but the nucleus, protons, and neutrons were largely unknown. The idea of harnessing energy from the atom, rather than simply observing its emissions, was purely theoretical, bordering on science fiction. The prevailing scientific paradigm was focused on understanding the atom's structure and the nature of radioactivity as a spontaneous decay process, while physicists like Marie Curie and Ernest Rutherford were probing the atom's secrets. The possibility of controlled artificial nuclear reactions was beyond the horizon of imagination. Von Bayer's footnote was a philosophical musing, not a scientific prediction based on empirical evidence at the time. The scientific community, engrossed in the immediate challenges of understanding radiation's properties and biological effects, largely ignored the speculative aside. Von Bayer himself seemed to treat it as such, moving on to other research without further elaboration. The paper was published in the proceedings of a respected scientific society, but its footnote held no immediate sway. It was a seed planted in infertile ground, awaiting a future season. The next 2 decades saw seismic shifts in physics. The development of quantum mechanics and the discovery of the neutron by Chadwick in 1932 fundamentally altered our understanding of the atom. The concept of the nucleus solidified, and scientists began to grasp the immense forces contained within. Einstein's famous EXMC2 equation, published in 1905, provided the theoretical framework for mass energy equivalence, though its implications for nuclear energy were not immediately apparent. By the late 1930s, the landscape had changed dramatically. The discovery of nuclear fission by Hahn, Strassmann, and Meitner in 1938 provided the missing link. They demonstrated that heavy atomic nuclei, like uranium, could be split, releasing enormous amounts of energy and a cascade of neutrons, potentially leading to a chain reaction. Suddenly, von Bayer's 1911 speculation wasn't so fanciful anymore. It was in this charged atmosphere, with the looming threat of war, that scientists began to seriously consider the destructive potential of nuclear fission. The energy released in fission, they realized, aligned with the colossal energies von Bayer had vaguely alluded to. His footnote, once a theoretical curiosity, was now being re-examined through the lens of a terrifying new possibility: the atomic bomb. The scientific community's focus shifted from pure discovery to the urgent, often clandestine development of nuclear technology. Figures like Leo Szilard, who conceived of the nuclear chain reaction in 1933, became central. The theoretical groundwork laid by decades of research, including von Bayer's early, almost accidental, contemplation, was now being weaponized. The Manhattan Project, initiated in 1942, was the culmination of this effort. Thousands of scientists, engineers, and technicians worked in secrecy to harness nuclear fission for military purposes. They built reactors, refined uranium, and designed the first atomic bombs, all predicated on the principles of nuclear physics that had been painstakingly uncovered over the preceding decades. Von Bayer's simple footnote, a mere 28 words, had inadvertently touched upon the core concept of nuclear energy release. While he could not have foreseen the specific mechanisms of fission or the geopolitical implications, his statement captured the essence of atomic power. It was a remarkably prescient, albeit unintentional, glimpse into the future of weaponry. This obscure observation serves as a powerful reminder of how scientific inquiry can lead down unexpected paths. The pursuit of knowledge, even in its most incremental forms, can yield insights with profound, unforeseen consequences. The history of science is replete with such footnotes, moments where a stray thought foreshadows world-altering developments. The journey from von Bayer's 1911 paper to the Trinity test in 1945 is a testament to scientific progress and its inherent duality. The same understanding that could illuminate the world also held the power to destroy it. This single sentence, overlooked for so long, now stands as a quiet monument to that complex legacy. The implications are stark. The foundations of a weapon capable of unprecedented destruction were, in a way, articulated even before the fundamental particles of the atom were fully understood. It highlights how theoretical speculation, even when seemingly detached from empirical data, can resonate through scientific history. Consider the scientists working on the Manhattan Project. They built upon decades of accumulated knowledge, a chain reaction of ideas stretching back to the dawn of atomic physics. Von Bayer's footnote, though likely unknown to most, was part of that unbroken lineage, a whisper from the past echoing in the labs of Los Alamos. The report itself, in its original German, is a testament to meticulous scientific practice. Yet, it's this single, almost poetic speculative sentence that captures our attention today. It reminds us that scientific progress is not always linear, and breakthroughs can emerge from the most unexpected corners of research. The story of von Bayer's footnote is a lesson in scientific humility and the unpredictable nature of discovery. What seems like a minor detail or a theoretical tangent can, with time and changing scientific understanding, reveal itself to be profoundly significant. It underscores the importance of preserving even the most obscure records. Ultimately, the 1911 report on X-rays serves as a quiet marker in the long, complex history of nuclear physics. It's a reminder that the path to understanding the atom and its immense power was paved with countless observations, experiments, and even fleeting, speculative thoughts. The atom's power was unlocked through decades of dedicated scientific endeavor. But sometimes the most profound hints of what was to come can be found in the quietest of places, like a footnote in a forgotten paper from 1911. The archive continues to yield its secrets.